Quantum Mechanics and the Conduction of Electricity, from Wave Functions to Photons. An A&D Theory Perspective. In 1897, J. Thomson discovered the electron. Just 3 years later, Paul Drude published the first microscopic theory of moving electricity. He imagined electrons inside a metal as a kind of gas, colliding with the fixed ions of the lattice. Hendrik Lorentz soon refined the picture, building what we now call the Drude-Lorentz theory. It was the first attempt to explain electrical conduction in terms of the electron itself, a remarkable step, though one that would soon give way to the abstractions of quantum mechanics. Quantum mechanics tells us that electricity is not carried by real particles passing energy along a wire, but by wave functions, mathematical objects that live in a Hilbert space of infinite dimensions. Dwell for a moment on the term infinite dimensions. What does it mean? In the whole of our universe there exist only 3 spatial dimensions: length, breadth, and depth. In all of human history, no one has ever described or detected a single extra spatial dimension. Yet, in the mathematics of quantum mechanics, electrons in a conductor are said to live in an infinite-dimensional Hilbert space. This is not a minor detail. It means the very framework of explanation exists in a realm entirely removed from the physical dimensions of our universe. Infinite dimensions, what does that mean? And why should such abstractions be trusted to explain the flow of electricity through an ordinary wire? Can we accept such a paradigm? Each electron is smeared into a probability cloud, overlapping with every other, and the current is explained as a subtle reshuffling of these overlapping distributions. The wave function itself is not a physical wave. It cannot be touched, measured directly, or even said to be real. It is simply a tool for calculating probabilities. Yet it is expected to describe the exact delivery of energy from electron to electron without ever missing its mark. We are told that standing block waves in a crystal lattice somehow conspire to shift under a voltage, producing a collective drift. But here's the rub: waves in nature dissipate. They spread, they lose energy, they fade. A standing wave is the least likely candidate to deliver energy with pinpoint precision. And yet, quantum mechanics insists that a wave function, unlike every other wave we know, never decays. It is kept pristine by mathematical decree. The result is a theory that explains electricity not by physical cause and effect, but by the bookkeeping of amplitudes in an abstract space far removed from real wires, real electrons, and real energy transfer. Introducing the Augmented Newtonian, and theory of electrical conduction. This theory bypasses the complexities of quantum mechanics by starting from simpler foundations. The electron is a particle in its own right, while the photon is a wave particle, a massless electric dipole. Quantum mechanics states unequivocally that photons are merely excitations of the electromagnetic field. But this is a cumbersome picture. To implement it, one must describe the field at every point in space, giving it infinite degrees of freedom. Photons are no longer real carriers of energy, but bookkeeping entries in a Hilbert space, created and destroyed by field operators. The result is a system of dazzling mathematics, but no clear physical mechanism. By contrast, theory restores photons to their natural role, particles that move, connect, and conduct energy directly. However, according to Augmented Newtonian Dynamics, the electron is not a passive participant in a mysterious field but an active agent that always strives to keep its base energy intact. It achieves this by mediating its energy through the emission of pulses of electrical energy. When the electron has an excess, it emits a photon, and when it has a deficiency, it absorbs one. In this way, the electron self-regulates and preserves its core energy. These pulses naturally form into a stable dipole configuration, and that configuration is the photon itself. By granting the photon a physical structure, Augmented Newtonian Dynamics overcomes several paradoxes left unresolved by quantum mechanics. It explains how electrons can generate photons of any wavelength or frequency on demand, and, crucially, do so in only a few femtoseconds, the unimaginably brief timescale required for the functioning of today's high-speed electronics, lasers, and quantum devices. In this picture, the electron is no longer a mere intermediary of an abstract field but the true architect of photon emission and absorption. In this picture, electricity in a wire is conducted not by abstract wave functions but by real photons, exchanged from electron to electron. But if the explanation is so straightforward, why was it not adopted by quantum mechanics? The reason lies in the classical concept of recoil. A free electron emitting a photon would be kicked backwards, and across countless electrons such recoils would create chaos instead of conduction. If conduction were explained by electrons emitting photons in the ordinary way, every emission would kick the electron backwards with a recoil. For a photon of just a few electron volts, the recoil speed is calculated to be thousands of meters per second. Multiply this across the countless electrons in a conductor, and the result would be chaos. electrons flung into wild motion, energy spraying in all directions, and currents impossible to sustain. Carried to its logical conclusion, the numbers even imply superluminal accelerations, which physics forbids. This recoil paradox was one of the reasons physicists abandoned the idea of photon exchange and retreated instead into the abstractions of the wave function. And theory resolves the recoil paradox in two simple ways. First, the photons involved in conduction are the lowest energy photons an electron can emit, what we call conduction photons. Their energy is only about 1 electron volt. At such energies, the recoil on an electron is considerably reduced. Second, there is no net momentum, because emission and reabsorption occur on timescales so brief that the usual conservation laws of classical physics no longer apply. By the Heisenberg uncertainty principle, energy and time can fluctuate for intervals so short that the process escapes macroscopic constraints. In this way, photon emission and absorption by electrons in a conductor becomes not only possible, but precise, a mechanism far simpler and more physical than the abstractions of wave functions in infinite dimensions. Next, let us look at how current flows in a wire carrying direct current and alternating current. At room temperature, the conditions inside a conductor are highly chaotic. Free electrons travel in all directions at speeds greater than 1,000,000 meters per second. When a difference of potential is applied across the wire, a voltage is established, and electrons begin to exchange photons. According to the Heisenberg uncertainty principle, as it applies to energy and time, if an interaction occurs in a sufficiently short interval, it can involve any amount of energy, while if the energy involved is very small, the interaction can extend for an arbitrary time. This principle allows a free electron to emit and reabsorb a special kind of photon, which in theory calls a conduction photon. Free electrons cannot emit photons of arbitrary type or energy, only photons with the precise energy, wavelength, and frequency associated with conduction. The reabsorption must occur within the interval defined by the uncertainty relation, which for conduction photons works out to about 10 to the power of -15 seconds. Consider what happens inside a conductor under chaotic conditions. Let us call one electron electron 1. It emits a photon, call this photon 1. In the turbulence of the electron C, electron 1 cannot reabsorb photon 1. Instead, it absorbs a different photon, photon 2, which had been emitted by another electron, electron 2. This exchange continues across the conductor. But what happens to photon 1? Every electron is already occupied, each matched to a photon, so photon 1 cannot be reabsorbed inside the conductor. It leaves the metal and loops back to re-enter it from outside. As it does so, photon 1 enters the virtual photon ether, where virtual photons align into chains that guide the real photon's motion. These chains form what we see macroscopically as the familiar lines of force surrounding a current-carrying conductor. Each line of force, though built from countless virtual photons, carries the energy of just a single conduction photon, about 1 eV. In this configuration, the lines of force are said to be in series. In a direct current, a difference of potential applied across the ends of a wire establishes a voltage along its length. Inside the conductor, electrons are already in chaotic motion at speeds of millions of meters per second. Under the influence of the voltage, this motion acquires a small bias, producing a net one-directional flow known as the drift velocity. The drift is extremely slow, only fractions of a millimeter per second, but it is steady and coordinated. The forward motion of each electron is continually disturbed by collisions with the crystal lattice of the metal. These repeated interruptions define what physicists call the mean free path, the average distance an electron travels before it is scattered. In the case of an alternating current, the drift velocity of the electron is no longer seen. In this picture, the electron appears frozen in place, it does not move at all. So this proves that it is definitely not the electron that is the carrier of charge, it is photons that are the charge carriers. For over a century, electricity has been described through the abstract mathematics of quantum mechanics. And theory takes a simpler path. It shows us that electrons are real particles, that photons are the carriers of energy, and that conduction is nothing mysterious, it is photons passed precisely, electron to electron, throughout the wire. The details may be debated, but the direction is clear. Sometimes the simplest explanations are the most powerful. And perhaps in electricity, as in all of physics, clarity lies not in more complexity, but in less.